Welcome back. This is Discrete Optimization Local Search Part 6. Okay. So what we're going to do today is start talking about this topic of escaping local minima. And we'll introduce a very important notion, which is connectivity, and talk a little bit about various neighborhoods and how they relate to this notion. The big goal here is that we are setting the stage for introducing techniques that will allow us to actually find higher quality solutions, not just producing, moves that are improving all the time, but allowing the search to do more interesting things. But a requirement, in general, is that you need some property of your neighborhood to do good things. Okay? So remember, what we did, what the guarantee that we have is we apply, greedy moves inside the neighborhood, is that when we complete the search, we are guaranteed that the value, that the configuration that we find is a local minimum, okay? So which basically means that if you are at that position in the space, if you look around, there is no place you can go which is better. That's what it means to be a locally optimum, okay? You can't move to a place which is better, okay? But that doesn't guarantee that this place is actually good in the grand scheme of things. There may be something really good somewhere else and you don't know how to get to it. Okay? So we have no guarantees for optimality, and therefore in practice escaping these local minima of poor quality is a very important issue. And once again in the next lecture we'll show you two really interesting techniques to do that. What we are doing today is setting the stage for that. Okay, so this is a beautiful picture done by Carlton, right? So you see this is kind of the neighborhood, the entire regions of the space. Okay, so you see, in this particular case, basically this neighborhood is colored into, cold and hot region, and hot means high quality, cold means terrible, right? And so local search starts from a point, you define the neighborhood of that point, and then what we have done so far is taking a direction which is improving, the move. And so we follow this, and then we can continue finding a path, and hopefully we get to a good region of the space. Okay? So that's what we have been doing so far. Okay? Now, the landscape of the objective function, okay, can be complex like this thing, right? So what you see here is the quality of the solutions, and we are minimizing, okay? So this is essentially all the possible solution, and this is the quality there, okay? And what you see here is that there are various local minima in that particular place, right? So this is a local minima, this is also a local minima. And this one is actually pretty interesting. That's the global minima. Okay, so that's the global minima in this particular case. So we want to get there, but the search that we have seen so far are not going to get you there, right? Now, one of the things that you really don't want to happen is this. Okay, so you can define your problem, okay, in such a way that it's not connected. Which means that if you start from that particular point, you can move inside that region, right? And find a good point in that region, which is here. But you have no way to actually get there. There is no move that will get you there. And that's terrible. The entire region here, which is where the good things are, is not accessible if you start from there. Okay? So we don't want that. This is not good. Okay, so we have no way from moving from one side of the neighborhood to the other one, and so we want to avoid that. And the connectivity requirements that I'm going to talk about is exactly avoiding this. Okay, so this is the definition, but essentially what it means is that you want to be able to go from any configuration to at least one optimal solution. Okay, so in a sense, you're going to say that a neighborhood n, and remember, a neighborhood is something which, given a configuration, is going to give you a set of configuration where you can go. Okay, so a neighborhood n is going to be connected if from every configuration S, anywhere. Okay, so there is an optimal solution O that you can reach by taking local move. And what is a local move? Well, you start from S. Okay, that's state S0. Okay, and then you can take a local move to go to S1, then to S2, to S3, and so on, up to Sn, which is the optimal solution that you're looking for, and every one of these configuration can be accessed by a local move, which basically means that Si is in the neighborhood of Si minus 1. Right? So this is the definition of connectivity. Intuitively, it's very simple. It basically means that you can apply local move from any configuration to get to the optimum. It doesn't mean that you will get there, right? It just means that there is a path, okay? Afterwards, we have to find that path. But what we know is for sure there is one path to an optimal solution. Okay? Now, connectivity doesn't guarantee optimality, as I just told you, right? Because so far, all local search have been greedy, okay? So what happens when you are greedy, okay? When you are greedy, let's say this is the starting point when you are there, you're going to you're going to take moves that are basically improving, okay? So, and if you take moves that are improving, you're going to get to this local minima, okay? So you take another point over there, beautiful point, you go down, that's where you get. You don't get here, right? Because if you try to improve all the time, you're not going to get there. You would have to go up the hill and then go down, right? Which is not something that we have been able to do so far. And obviously, you have all these points here that are basically bringing, oops, I want to show you that because they're so beautiful, right? So that are going to all these places, but they don't get to the global optima. Okay? So in a sense, connectivity doesn't guarantee optimality, but it's still a very good property to have, because once we introduce some of the techniques that we'll see in the next lecture, in connected neighborhood, you have more hope, and actually in some cases you have guarantees to get to the actual optimal solution. So what you see here is graph coloring. Remember, we had this beautiful problem where you had to color all these vertices such that two adjacent nodes were had to be colored by a different color. Okay, so and the neighborhood that we chose was very simple, right? It was changing the color of a node. And obviously that neighborhood is connected. And I'm going to give you a simple algorithm, and this is actually very interesting because we are cheating like hell. But this is what you do when you want to show that something is connected, right? So what you have to do is you start from a configuration and you have to show a path, that indicates that brings you to the optimal solution. But we can do a really nice assumption. We can actually postulate that we know the optimal solution. So if I know the optimal solution and I'm in a particular configuration, I can design a very simple algorithm to get to the optimal solution. What do I know? I look at every node, and if that node, doesn't have the right value, that means that its value is different from the value in the optimal configuration, I simply assign it the value which is its value in the optimal solution. So I do that for all the nodes. These are all local moves. They are all legal, right? And then essentially I get to the optimal solution. So this is very easy, right? But all the connectivity proofs are like that. So you suppose that, you basically assume that you have the optimal solution. And then you have a particular configuration, and you show you can actually get there. Now, this is a very simple one, right? Some of them are very complicated, but this gives you the essence of these kinds of proofs, Now, remember car sequencing, So car sequencing, once again, we were scheduling these cars on the assembly line. There's the production unit that had to put this option while the car were moving, right? And we had to satisfy the capacity constraints on this production unit to make sure that we could put the options on the cars, right? So what we designed was this beautiful neighborhood, right? Where we would basically look at the car and swap them, And here you see the options of the various cars, So we had a swap neighborhood, and this swap neighborhood is connected, And why? Well, let's look at the algorithm. So actually, let's go back and look at the sequence, right? So we can take this sequence and look at all the values, and either you have the right type of car there, or you don't, If you don't have the right type of car, what are you going to do? Well, there is your type of car somewhere inside the sequence. You can swap them, and now, what do you have? Well, the first slot is right. You move to the next one, The next one you say, well, you look, is it right or not? Is it the value that you have in the optimal solution? If it is, fine, you move to the third one. If it's not, you look for the right type of car and you swap these two things, And so you can continue doing that, and that's how you show connectivity, So once again, that's what you see there. You have an algorithm which iterates from, the first to the last slot of the assembly line. Then you look, essentially, is the value for the configuration S, SI, is the same as the value of that part of the slot at, at position I in the optimal solution. That's OI. If they are different, what you do is you look for a particular configuration inside a particular type of car inside the sequence S, and further away, obviously, which is of the same time as the value which is inside the optimal solution, and you swap these two things. And you continue like that, and obviously you know that you will find one, right? Because it's in the optimal solution. And therefore, you swap all these things, and you get an optimal solution at the end. So what I'm showing you here is essentially by doing swaps, you will always get to the optimal solution by a sequence of moves. Now, once again, I want to repeat this. It doesn't mean that your algorithm is going to find that sequence, right? Because we are always trying to find improving moves and things like this. We will have to do other things. So in practice, some of these steps here are maybe degrading tremendously the quality of your solution. And that's what is the challenge in local search, right? So let me look at something which is a little bit more complex, right? So this is the traveling salesman problem. Remember, we had all these cities, okay, that we had to visit exactly once, okay, and trying to minimize the total distance. And we introduced this simple neighborhood. That's one of the simplest one that we introduced was to-opt. Now remember, to-opt was basically taking two edges and replacing them by two other edges, okay? And the question that you may ask yourself is that, is this neighborhood connected? Okay, it's a very simple question because it has only two possible answers, right? Yes or no. So think about it. Is it connected or not? So to actually find that out, so look at this thing. Okay, so look at this particular tour. Is there another way to view this? Well, first let's start numbering these guys. So we have all the vertices and the name of these vertices. Okay, and now a tour, you see the tour, you know, starting from 1, moving to 5, then to 9, then to 10, then to 6, 3, and so on. Okay, so when you look at this tour is really like a sequence, right? So you see the sequence here, you know, 1, 5, 9, 10, 3, and so on. Okay, so basically a tour here can be viewed as a sequence, right? Now remember what to-opt does is removing two edges and replacing it by two other edges that you see over there, right? So I have a sequence here, and what is going to be my sequence for this thing? Okay, so essentially what you know is that in this tour, right? So you were basically going to 6 and 6 was going to 3, right? So what we're going to do is remove this and replace it by an edge to 7. And then we're going to revert essentially all these edges that you see on that right side and then connect that with an edge going from 3 to 2. So we are basically taking these things, okay? So the edges that we are removing in the edges going from 6 to 3, okay? So this is the edge that you see somewhere here, okay? And then we have to revert that. So we are basically reverting the sequence. So what you really get there is that particular sequence there, okay? So you see the original sequence over there, and you see the sequence which is here, which is essentially the same sequence as we have here, except that we revert all the ordering. We basically reverse that particular sequence, right? And that's what you see over there, okay? So essentially what I'm telling you is that to-opt can be viewed on sequence, and you isolate a subsequence here, and what you do is you basically reverse it. But keep it the same position, but reverse it, okay? Now, instead of moving from 6 to 3, you move to 6 to 7, and then to 11, and 8, and 4, and so on. And that's what you see over there, right? So essentially what you do is you select a subsequence, and you reverse it, okay? Now, I'm asking you the question, is this neighborhood connected or not? Okay? Well, we can use a very simple algorithm again, right? If we know the optimal solution, okay, and we can postulate that we know it, and we have a configuration right now, what are we going to do? Now assume that, for instance, this guy is the optimal solution, okay, which is probably not the case, but never mind, okay? But if we look at this thing, what we're going to say, okay, so, we have 1, 5, 9, 10, 6, and this is the same as this in this supposedly optimal solution. But then we see here there is a difference between these two guys, right? There is a difference, okay? So there is one which is starting at 3, okay? This subsequence is starting at 3, and that one is starting at 7, okay? So what do we do? Well, we say, okay, so I'm going to select a move. By what? Well, I want a 7, right? So this is what I want, okay? And I have a 3. So I'm going to look until I find a 7, and then I'm going to apply a to-opt. And that to-opt is basically going to revert that sequence, okay? And I will obtain this tour now, okay? And what is nice about this now is that, I can move to the next element. So this is all correct, okay? And then I can move inside the sequence and try to do the same kind of things for the subsequent vertices. So in a sense, what I'm just told you is that I have a very simple algorithm, okay, which go to the various elements of the sequence, very much like I did for the car sequencing example. And if a particular value in the tool that I'm considering now is not the same as the value in the optimal solution, I find a subsequence starting at I, which basically ends with the value in the optimal solution, with the city inside the optimal solution, right? So I have a subsequence now, and what do? I reverse it, okay? And that's what you see over there. So I go up to Si, I take the sequence which brings me to the particular point that I wanted, I reverse it, so I start with that guy, which is now correct. I have all the sequence which is there, and I have my new sequence, which is correct not only up to Si minus 1, but now also to Si. Okay, and I continue doing that until I find, until I get to the optimal solution. So once again, very simple algorithm to move from a particular configuration to an optimal solution. Okay, now. I'm going to leave you with an interesting homework. Remember the TTP, the traveling Turnman problem? Okay, so I will show you this beautiful neighborhood, right, with 5 moves: swap home, swap teams, swap rounds, swap partial teams, swap partial home. Okay, the question for your homework is essentially, is this neighborhood connected? And if you find the answer, okay, call me. You can call me if you find the answer. I'm very interested in knowing if you actually can find the answer to this particular problem. Thank you very much. See you next time.